For a very long time, we believed the adult brain was a fixed and finished structure. This idea suggested that our core abilities, our personality, and our intelligence were set in childhood, then permanently set in stone. Early attempts to understand the mind, like phrenology, treated the brain as a static map of predetermined traits. Even pioneering work in the 19th century, which correctly linked specific brain regions to functions like speech, reinforced this notion of a hardwired machine. The great neuroanatomist Santiago Ramón y Cajal, who established that the brain was made of individual cells, famously declared that in the adult brain, nerve pathways are fixed, ended, and immutable. This dogma cast a long shadow, making the prospect of meaningful, lasting change feel unreachable, a distant lighthouse in a dense fog. But today, we know this view was profoundly wrong. The revolution began with landmark experiments, like those by Michael Merzenich, which showed that the cortical maps in adult monkeys could literally be redrawn through experience and training. This discovery paved the way for therapies that help stroke survivors reclaim lost function by forcing the brain to rewire itself. Studies of phantom limbs further revealed that the brain's maps are not fixed, but dynamically reorganize in response to changes in the body. The brain is not a static object. It is a living, dynamic landscape, constantly changing in response to every experience. We call this fundamental property neuroplasticity. It operates through several mechanisms. There is structural plasticity, where the brain physically changes by growing new connections between neurons, a process called synaptogenesis. The very shape of neurons can change as they grow or shrink dendritic spines to strengthen or weaken connections. And there is functional plasticity, the brain's ability to shift functions from a damaged area to an undamaged one, like traffic rerouting around a closure. The brain can even change the thickness of the myelin sheath around its pathways, altering the speed of communication to optimize performance. Modern technology allows us to witness this process directly. Functional MRI, or fMRI, shows us how brain activity shifts as we learn new skills. Diffusion tensor imaging lets us map the brain's physical wiring, revealing how those pathways strengthen and change over time. The evidence is all around us. The brains of professional violinists dedicate more cortical territory to the fingers of their left hand than those of non-musicians. London taxi drivers, who must memorize the city's labyrinthine streets, develop a significantly larger hippocampus, a region crucial for spatial memory. We've even discovered that in specific regions like the hippocampus, the adult brain can grow entirely new neurons, a process called adult neurogenesis. This means your experience, your thoughts, and your actions are constantly, physically, reshaping the organ that creates them. Who you are today is not who you must be tomorrow. Your brain is the vehicle for your life, and neuroplasticity means you are always learning how to drive. This is a fundamental principle of modern neuroscience, not a self-help platitude. Change is not just possible, it is the biological constant of your brain. By understanding the mechanisms that govern this change, you begin to gain access to the operating manual for your own mind. The static world of the past is gone, replaced by the discovery of a dynamic, evolving universe inside your skull. Imagine the mind as a vast forest. Every thought you have, every skill you learn, and every habit you form begins to cut a path. At first, it's barely a trail, like learning the first words of a new language. These initial steps are slow and demand intense focus. Each mental effort makes the way just a little easier for the next time. But if you never return, the forest reclaims its territory. This is disuse-driven pruning, where unused connections are cleared away. Walk that path daily, however, and it becomes clear and wide. This is use-dependent strengthening. Your habits, good and bad, are simply your most traveled routes. Breaking a habit means consciously choosing to let the old trail overgrow, while you blaze a new one, step by difficult step. Now, let's scale up this idea to a vast, dynamic national highway grid. In the beginning, our brains are mostly dirt roads, countless potential routes, but travel is slow and inefficient. Repetition is traffic. The more you use a specific mental route, like practicing a piano scale, the more traffic it gets. The brain responds to this demand by paving the road, adding lanes, and installing expressways. Mastery is a multi-lane neural highway. It's the effortless flow of information that allows a musician's fingers to fly, or a fluent speaker to converse without translating in their head. The thought travels so quickly, it feels automatic. But if you starve an old route of traffic, it decays. The brain's maintenance crews, specialized cells called microglia, actively dismantle the unused infrastructure, freeing up resources for highways that are in demand. To change, you must consciously and persistently redirect the traffic. There will be setbacks, but the key is to keep routing your mental energy onto the new, desired roads. This isn't just a metaphor. It's a physical reality governed by a simple, elegant principle. In 1949, the psychologist Donald Hebb summarized it in a phrase that would define modern neuroscience. Neurons that fire together, wire together. Every time two neurons are activated in sequence, the synapse between them gets a little stronger. With enough repetition, the communication becomes faster, more reliable, and more likely to happen again. Conversely, if they fall out of sync, the link weakens and eventually fades. This microscopic rule drives macroscopic change. It's the fundamental law that allows you to learn, to forget, and to consciously reshape the person you are. Decades before Hebb, the Spanish neuroscientist Santiago Ramón y Cajal first mapped this neuron forest. He established that the brain was made of discrete cells and prophetically hinted that the connections between them were not fixed, but could change with experience. Later experiments proved him right, showing that animals raised in enriched, stimulating environments developed thicker cortices, physical proof that experience alters brain structure. And today, modern imaging technologies like fMRI make this plasticity undeniable, allowing us to watch in near real time as the brain's maps are redrawn through training and intention. To understand how we rewire our brains, we must zoom into the microscopic space between neurons. They never physically touch. A minuscule gap, just 20 nanometers wide, separates them. This is the synaptic cleft, the fundamental arena where change occurs. It all begins with a signal, an electrical impulse called an action potential, racing down the axon of the sending neuron. As this spike arrives at the terminal, it triggers specialized gates, voltage-gated calcium channels, to swing open. A flood of calcium ions rushes into the cell, acting as a critical messenger. This influx of calcium activates a sophisticated molecular machinery, including proteins called snares. They act like docking ropes, pulling vesicles filled with chemical messengers, neurotransmitters, to the edge of the cell. The vesicles fuse with the membrane, spilling their contents into the synaptic cleft. These neurotransmitters drift across the tiny gap and bind to specific receptors on the receiving neuron, like a key fitting into a lock. Excitatory messengers like glutamate bind to AMPA and NMDA receptors, preparing the neuron to fire. Inhibitory messengers like GABA bind to their own receptors, telling the neuron to stay quiet. This binding opens channels, allowing charged ions to rush into the receiving cell, changing its electrical state. If enough excitatory signals arrive close together, they build up, triggering a new electrical impulse in the receiving neuron. The message has been passed on. This entire intricate sequence unfolds in less than 1,000th of a second. When a synapse is used repeatedly, it strengthens. This process, known as long-term potentiation or LTP, is the cellular basis of learning and memory. The connection becomes more sensitive, with more receptors and a greater release of neurotransmitters. This isn't a two-cell story. Nearby glial cells like astrocytes also participate, managing neurotransmitter levels and providing energy, forming a tripartite synapse. But what orchestrates this structural growth? A key player is a protein called Brain-Derived Neurotrophic Factor, or BDNF. Think of it as a potent fertilizer for your neurons. BDNF promotes the survival, growth, and complexity of neurons. When released, it binds to its own receptor, TRKB, kicking off a chain reaction inside the cell that activates pathways like mTOR. This signaling cascade tells the neuron to build new structures, to form new connections, and to strengthen existing ones. It is the molecular engine that turns fleeting electrical activity into lasting physical change. Crucially, we can influence our BDNF levels. One of the most powerful triggers is aerobic exercise. Even a brief, brisk walk can acutely boost BDNF production, priming the brain for learning and making it more receptive to change. When you engage in effortful learning or physical activity, demand signals travel to the neuron's nucleus. There, they activate the BDNF gene. The genetic code is transcribed into a mobile blueprint, messenger RNA, which then travels out of the nucleus. In the cell's cytoplasm, ribosomes read this blueprint and translate it into the BDNF protein. This newly synthesized protein is then folded, processed, and packaged into vesicles for transport. It's sent precisely where it's needed most, to the active synapses that are driving the learning process. Its release there sends an unmistakable signal. This connection is important. Strengthen it, grow here. Beyond exercise, other lifestyle factors like intermittent fasting, exposure to sunlight, and a diet rich in omega-3 fatty acids have also been shown to elevate BDNF. By understanding these levers, we gain the ability to consciously enhance our brain's natural capacity for growth and adaptation. The 2026 Rewire protocol uses 3 tools: simple, inexpensive, immediately actionable. Break autopilot to redirect attention and choice. Small surprises detour traffic from old highways. Short, focused bursts, spaced across the day. Each burst is another pass down the new path. Sleep replays practice, stabilizes and integrates memory. Night is when your brain paves the new highway. Pattern interrupt. Micro-learning, sleep, repeat daily. Add a short walk, pre-practice. BDNF primes plasticity. 5 words here, 1 minute there, compounding gains. Protect sleep. It's essential to lock in progress. Wake to a slightly clearer path and smoother highway. Consistency is the architect of identity. Direct the flow, and your brain follows. Begin with one tiny skill. Observe the shift. Take the 7-day Rewire challenge. 5 focused minutes, morning and afternoon. Move a little, then learn a little. Sleep well. Let consolidation do its work. Notice the easier step, the faster signal. Your brain is living, adaptable, yours to guide. Change is your biological birthright. Start today.